Hi everyone, I'm Manish Jain, the founder and CTO of Dgraph Labs, and I'm really excited to welcome all of you to the first ever Dgraph Day. I would also like to thank Dgraph's marketing team for helping put together this event and made it available via live stream to everybody around the world. So, welcome. And before I go further, I would really like to thank the open source community that has made Dgraph the most popular open source graph database out there. Um, this started off as a small project that I ran, that I started back in 2015, and it has grown into this thing where we have hundreds of contributors around the world. We have built a company of 50 plus people, and we are seeing a huge traction around Dgraph. So I would really like to thank all of the open source community who has helped us by contributing to Dgraph, who have helped us by providing feedback, by running Dgraph, by helping test Dgraph system, by contributing to the documentation, everything that you guys have done over the last 5 years. I would really like to thank you because all of those efforts are what made this event possible today. Dgraph's journey in open source started in 2015, as I just mentioned, but Dgraph's real journey started back at Google in 2011. My own journey at Google started in 2006 as an intern, and I joined Google in 2007 as a full-time employee working on web search infrastructure. And for the first 3 years, I was helping build a real-time distributed one of the biggest real-time distributed systems at Google, which was building an incremental indexing system, so we could, from the time we see a web page to the time we serve it, we could really reduce the amount of time it takes. And so I learned a bunch about how do you work with big, large real-time distributed systems. And Google then happened to acquire a company called MetaWeb, who brought Knowledge Graph to Google. And I started to look at Knowledge Graph to see how we could use it in web search. Now, this is before Google started answering queries. This is the times when Google was still only serving blue links for every query. And so we sort of like put together a team to be able to build Google's first graph indexing and serving system, and I happen to be one of the tech leads of that project. And the idea was that we had all of these fragmented backends like weather and events and movies and flights and so on and so forth, spread all over the company, run by different teams, just because they had different data models. So each data model ended up having its own backend, and the backend had to be ran and maintained and so on and so forth. So the idea was to be able to unite all of those different data models and backends into a single graph indexing and serving system. And the system had to be hit by a good chunk of web search queries. So it had to be performant, it had to be scalable, it should not have a single point of failure. And when you're hit by web search, you really like have to think about the latency requirements and the throughput requirements of the system. So we put together a system which was low latency, high throughput, and could do arbitrary depth joins, so could run arbitrary depth queries. So we can traverse the relationships between all of these different data models which existed, and be able to serve knowledge to the world. And so I learned a bunch about how you could build a sort of, web scale graph serving system, and that's the knowledge that sort of inspired Dgraph. Now, Dgraph is obviously inspired by all the work that we did while building the distributed graph serving system, but it is not just a graph serving system, because outside of Google, when we were building Dgraph, we decided to build a distributed graph database. So we took ideas from the graph serving system at Google, but then also married it with a lot of ideas that we took from another project at Google called Spanner, which is their geographically distributed SQL database. And we brought a lot of the good ideas from there, like distributed ACID transactions, synchronous replication, strict consistency guarantees, fault tolerance, and so on and so forth. So all of that stuff, which was pioneered at Google, we also took a lot of inspiration from there and brought that into Dgraph. And then finally, we just had a lot of research that we did ourselves in Dgraph Labs, because there was no one paper that we could follow to build this distributed graph database. A lot of this is very unique, and so we had to build up on the ideas that we had learned before, but then bring in new ideas to be able to build this really unique system, which can scale like a NoSQL database, and which can do the distributed transactions and consistency like Spanner, but then really execute these complex graph queries like no other system out there. And so if you look back at what we were trying to solve at Google, we had this big problem of the knowledge graph. Now let's look at what knowledge graph is. Knowledge graph has lots of knowledge, lots of data types, in fact, thousands of data types into a single system, into a single sort of like data store, if you will. We have thousands of data types, and each of these data types have hundreds of properties, and these properties are not always defined. They are sort of sparse. Sometimes they are defined and sometimes they are not. And so serving thousands of different data types with hundreds of sparse properties is not something that existing systems or existing databases in the market are well suited for, right? And so what happened was each of the backends that was designed to serve what they call one boxes. One boxes are sort of like knowledge, limited knowledge backends, if you will. So if you were to search for weather in San Francisco, you get shown the weather in San Francisco, which is actually not. I mean, there are obviously web pages below it, but at the top, what you see is the weather. You see the Fahrenheit or the Celsius right there, and that's a one box that gets triggered because the Google engine understands that you're looking for weather, and it routes it to the right one box to show you the information without having to click on a blue link. So what we had at Google was that we had lots of backends with different data models, each serving one kind of data model, and then the web search had to iterate over each of these backends to be able to serve the corresponding one box. But the problem was that it is fragmented, and so you have to maintain all of these different backends separately. And secondly, you cannot query across any of these data models because they are very different silos of information. So the kind of complex queries that lets you say something like, well, when I land in New York, recommend me an event to go to, that requires you to figure out the flight information, to figure out when you would land. Then it requires you to figure out the weather at that time. And then depending on whether it's raining or it's sunny, you can find the events which would be very well suited to that. And so in a single query, you are traversing three different essentially data models to be able to answer that query. And that kind of sort of ability to query that was just not available at the time. And so what we wanted to do was to build a single service system which could operate upon the relationships and be able to query these by traversing the relationships and so on and so forth, and infer unique, interesting data points. And that required us to build a graph serving system. Now, it might be tempting to say that you need a graph system if you have to serve knowledge graph. It makes sense, but this problem of data modeling is not limited to just knowledge graph. In fact, this problem of data modeling complexity is everywhere, and you see this echoed in different blog posts by different companies. I've been reading blog posts from Facebook and Twitter and Dropbox, Airbnb, LinkedIn. They all had to go build custom graph solutions. Not everybody is serving a knowledge graph. So why do they need that? The problem is that the existing solutions, which are non-graph based solutions, they are not very good if you were to introduce new data models which are related to existing data models, and be able to run queries with them at scale. Also, you have to modify your code to be able to deal with these introduction of new data models. So every time you introduce a new data model, you might have to change your app. You might have to migrate some data. You might have to re-architect how the schema is, and so on and so forth. And that is hard. That is hard, particularly at scale. And so to solve for data modeling complexity, a lot of companies want to use or end up using a graph solution. Now, if there was existing graph solution which would work really well, they would all go and use that. But that's not the case. The problem is that we don't have a really great graph solution in the market, or at least we didn't before Dgraph. We didn't really have a great graph solution in the market which could scale well, right? And all of these companies needed something which could really scale to terabytes of data. That just did not really exist. The second problem was that a lot of these graph solutions in the market are not general purpose. They're designed for very specific graph problems. And the moment you venture out of those graph problems to do something as simple as searching on full text or doing regular expression queries or just matches of strings and regular things that you would expect to do in a typical SQL database, they just don't exist in the existing graph in the existing graph solutions. So you can't operate on a broader set of data problems. You imagine sort of a SQL database without indices, right? It would work. It would still be able to do something, but it would not be able to do a lot of things, and that would limit the how many use cases you could throw at that system. And that is the problem with that was the problem with the graph ecosystem. And the third problem that I saw with the ecosystem was just accessibility to modern developers. The languages used by graphs were just not mainstream. They were very research focused, and in fact, they were being used for doing very research focused analytics, and some of these things were just not legible for modern developers, which made graphs even more scary than they needed to be. And so these are the three big problems that I see, or I saw when I started Dgraph, is that they were not general purpose, they were not scalable, and they were not accessible. That's when I thought about building Dgraph. Right? And Dgraph is designed to solve all three of these problems. First, scalable. Dgraph is scalable to hundreds of servers and terabytes of data. This is something that we had to design for at Google, and that part of the design and the ideas from there, we were able to. They were the guiding light, the pole star for us when building Dgraph. So the D in Dgraph stands for distributed, and we always made it so that it's part of our open source offering. It was never an enterprise feature like you might see in other databases, which don't start off as being distributed databases. But Dgraph was distributed pretty much from version, I think 0.2 was it, which was introduced maybe a couple of months since version 0.1. So Dgraph was distributed from the get-go, and and that was the pillar for us to build on. And second is Dgraph is a general purpose. We didn't limit Dgraph to just the graph feature set. We thought about what all would a user need to be able to build their app or their platform on Dgraph. what all stuff would they need? And so, we obviously did a lot of string based indexing, which is sort of pretty crucial for a lot of apps. We did full text search early on. We did regular expressions a bit later, I think. We did term matching, equality indices, hash indices. All of them actually went in very early on in the system. We also did support geo queries, which are not yet supported by very popular databases either. But that's another hangover sort of from Google days, because we needed to be able to search across locations, and so we took Google's S2Cell indexing library and built geolocation search on Dgraph in very, very early days. We also supported date time, floats, and ints, and we even supported a very unique data type called password, which we hadn't seen anywhere else. But we felt like the to be able to serve an app, you need to be able to store your user's username and password in the database in a very secure way. There are just too many hacks out there, and we felt like having a native way for people to store their passwords would just make things a bit more secure and make things a bit more accessible to developers. And finally, talking about accessibility, we realized that a lot of the graph languages were just not very readable. They're just not very accessible, and we were looking for a sort of like a modern language which could speak JSON and which could be easy to comprehend even to people who have never seen this before. And this was a time when GraphQL was introduced, and we felt like that's just the right language for us to build this database on. So pretty much in sort of October 2015, we were, if you go back and look at the commits of Dgraph, very much in like October or November 2015, we were already like introducing GraphQL into Dgraph. And if you guys might remember, GraphQL was a draft version of the GraphQL spec was put out by Facebook, I think in June 2015. So it was within like a few months that we sort of adopted GraphQL, and it's been a great journey with GraphQL. We ended up obviously forking it to make it to build Dgraph query language, which we were previously calling GraphQL plus minus, and to add a lot more power, a lot more sort of like database features into it. But then we also in 2018 or 19, we ended up supporting the official spec of GraphQL as well, because as you might know, GraphQL is everywhere. GraphQL is being used by a lot of companies, and it's just really become very popular. Again, I think other people see the same benefits of GraphQL that we saw back in 2015, is that it is just so accessible. And so by building a graph system focused around developer accessibility, we come to Dgraph, which can have a GraphQL-like query language and then can return results back in JSON. Both of them are extremely popular standards. And so the end result of all of this thought and effort that we have put into Dgraph is that Dgraph has become really popular. In fact, it is the most popular open source graph database in the market. We have 16,000 GitHub stars. We have reached 10 million Docker pulls. In fact, I think just a couple of weeks ago, and this is up from 3.6 million Docker pulls 6 months ago. So there's a big jump that we have seen in just the last 6 months itself. Similarly, we are seeing 2 billion queries executed on Dgraph clusters across the world every week. And that's up from around 500,000 queries executed per week just 6 months ago. Overall, we have seen 24 billion queries executed in the last 6 months. And that just goes to show how popular Dgraph has become and how important Dgraph has become to users who are using it as part of their production setup, as part of their source of truth database, where the user traffic is directly hitting Dgraph instances. And Dgraph is fast. Dgraph is an interesting mix between a graph survey system and a graph database, and it shows in the benchmarks. In fact, we ran benchmarks against the leading competitive cloud-based graph system, and Dgraph is at least 2 times to 20 times faster than the competition. Not only that, Dgraph executes queries which the other system is unable to. For example, in this case, IC09, we just could not make it run in the other system. It kept on running out of memory. But in Dgraph, it's a very complex query, and we were able to run this. We are planning to write a blog post about what we have done here, but this is just to give you a taste of the benchmarks and how fast Dgraph is compared to the leading competition. Now, as I mentioned, Dgraph is meant to be easy for developers. It's meant to scale, and it's meant to be general purpose. But that's not the end of it. You still have to run Dgraph, and we have been sort of focused upon making Dgraph easier and easier to run, to make Dgraph system itself accessible to our users. And part of that, of what we have learned, is that most users don't actually want to run Dgraph themselves and maintain Dgraph. And it's not just a Dgraph. A lot of users just don't want to run a database. And you can see this by the success of like cloud-based databases in the market. It's just easier when users don't have to run their own databases. And that was our vision, to go build Dgraph Cloud. Dgraph Cloud is the only cloud graph platform in the market. It allows anyone to run not just Dgraph, but a full-fledged graph platform. They get access to the database, they get access to GraphQL APIs, they get access to caching, Lambda functions for business logic, authentication, all the things that you need to run in your backend. They are all accessible via Dgraph Cloud. And it's the only only graph platform in the market which is designed to replace the entire backend stack. And that's what's really exciting, because we wanted to build, when we were designing Dgraph Cloud, we didn't want to limit it to just the database part. Again, we went back to the first principles and thought about what is it that the developers would need from a backend. And it's not just a database. It's also caching. It's also the ability to run business logic, authentication, etc. And so we really sort of like put all of them into one package, into one umbrella of Dgraph Cloud. And so if you look at the history of Dgraph Cloud itself, we sort of launched it last year, but every new region in the cloud, we had to go manually sort of run some things and make it available, and would take 2 or 3 days. And honestly, I feel like you're not in the cloud until it is self-service. And so we have put a lot of work into building and rebuilding Dgraph Cloud, so it provides a very simple way for developers to get going with both Graph and GraphQL technology. And part of that is to allow the users to be able to spin up their backends wherever they are, the closest public cloud data center or region that they are in, and put it right next to their apps. And so the focus of the Dgraph Cloud has been to make that part of it, to be able to spin up Dgraph in regions all over the world, to be fully self-service. So the user should be able to go in, choose a region of their liking, and click on launch, and be able to spin up a backend in under 2 minutes. So far, the Dgraph Cloud has only been available in 5 AWS regions, and today we are launching Dgraph Cloud to be available in 11 more regions, making it a total of 16 AWS regions all over the world. And as I speak, the team is probably trying to launch it in 4 more AWS regions, so that it will be a total of 20 AWS regions. And that required a huge redesign on our part, and I'm really glad of what the team was able to achieve. So let's look at some of the regions that Dgraph Cloud is available in. So available in California, Ohio, Oregon, Virginia, Canada Central. In North America, in Europe, it's available in Frankfurt, Ireland, London, Paris, and Stockholm. And in Asia Pacific, it's available in Mumbai, Seoul, Singapore, Sydney, and Tokyo. And then finally, in South America, it's available in Sao Paulo. And not only are we available in the 16 AWS regions, you can also be up and running with the Dgraph backend in under 2 minutes. And that's a significant achievement for us, and required us to rework the entire cloud architecture. The entire Dgraph team has been working really hard over the past few months to make it possible and to launch it just before Dgraph Day. And I'm really proud of all the stuff that we have done to achieve this. In the next coming weeks, we'll extend its availability to GCP and Azure so we can be present in the cloud and the region of our users' choice. In 2019, we decided to build the support for official GraphQL spec, which we launched in early 2020 under slash GraphQL, a cloud experience focused solely on the GraphQL developers. But over the past year, we have learned that our GraphQL users really want the power and the expressiveness of DQL. And conversely, the DQL users really want to expose part of their data via GraphQL. And so we rethought how these two work together and built a unified interface by which our cloud users can see both DQL and GraphQL schemas. Our users no longer have to choose between a GraphQL or a DQL upfront, or which mode Dgraph should run in. Instead, they can use both DQL and GraphQL at the same time. And so with that, we decided that slash GraphQL can just be called Dgraph Cloud. With Dgraph Cloud, our users can get the power of the graphs and the power of GraphQL all under the same Dgraph managed cluster. So whether they choose free, shared, or dedicated instances, all of these Dgraph clusters would support this unified approach to DQL and GraphQL. I'm really excited to show you all the stuff that we have built into the cloud. The team has been really hard at work over the past few months in unifying the DQL and the GraphQL interface in a way where it is intuitive and allows people to run both DQL and GraphQL queries at the same time. So let me go to my cloud instance here. And I'm running this site called the tweet site. It's something that me and a couple of other engineers put together to be able to find interesting tweets on and be able to showcase them. So the tweet site, as you can see, there's a bunch of data transfer, a bunch of queries. All of these metrics are now available to you on the dashboard, and we'll have more metrics coming in some time, including the ingress, egress, and so on and so forth. Now, one interesting thing that we did is that we used to have only the GraphQL schema here, but now we also have the DQL, which is the Dgraph schema here. And what we have done is that we have shown you very clearly how some of the GraphQL schema actually maps to the internal DQL schema. So if you look at this DQL schema, it's tweets.featured, and the reason is that is because we have type tweets and we have featured as a date time in the GraphQL, and so the corresponding predicate mapping internally is flagged as being used by the GraphQL over here. So if you then need to run interesting DQL queries, you know exactly which predicate to use to run those queries. And if you try to modify it, you know that you can't modify it over here because it's only editable in the GraphQL schema. So you can go back to GraphQL schema and let's say switch to UI mode, and I can go to featured, click on it, and I can change that to, let's say, array or lambda or month or whatever, right? So all of that is now possible. There's one more thing that we want to get to is to make these auth rules in GraphQL a lot easier to comprehend and also be editable via the UI, and that's something that we want to get to in the next quarter. One more thing that we have done is that, the GraphQL schema you saw, there's an auth over here, which is really advanced, but it's a bit not as intuitive. So we've added a cloud access control, which sits above the Dgraph database, and more at the cloud level. And you can use that to decide what you want people to be able to read or not. So if I turn off my read permissions here, what will happen is the tweet side probably would stop running. It will not be able to run um, because we have disallowed anonymous access to the backend, and this adds one extra layer of security above whatever Dgraph already supports. And the great thing is that because it's a lot more simpler, it is a lot more intuitive for users. So we hope that by having this, our users are able to really fine tune the access to their backends, and just rest assured that security is something, that their backends are secure, right? Now, what I'm going to do is I'm going to launch a new backend, and I hope to launch it in a interesting location. But before I do that, let me just talk about some of the different tiers that you see over here. The first one is the free instance. Then we have shared instance, and then we have dedicated instance. The naming is relatively sort of, I hope, easy to understand. But I'll start by explaining the free instance. Essentially, lets you run your Dgraph, gives you like a Dgraph backend, but it limits you to 1 MB of data transfer per day. So if you want to go beyond that, you can switch to shared, which costs you like $10 a month, and comes with 5 GB of data transfer for free included. And for any additional gigabyte of data transfer that happens, you get charged $2 a month. Both in starter and in shared, the storage is limited to 25 GB of data, and if you sort of go beyond that, then you come to our dedicated instances. Now, the shared instances are essentially running multi-tenant Dgraph clusters. So we have namespaces and so on and so forth, and that's how it allows us to make it available to our users for such a cheap price, or for free in this case. With dedicated instances, you get your own dedicated hardware, and the great thing is you can also choose which regions you want to run your instances in. So for example, we have all this long list of instances that are available. So let me run an instance, let's say in Sydney, and I set it to HC. I'll make it, I'll run on Jaeger as well, so I can see how my queries are performing. I'll set it to organization founder team. In Jaeger, you can also set the sampling ratio. So I'll set it like around, let's say, set it to 10%. Let's increase that to maybe 20%. Yep. I'll set a name for this is, and the subdomain would be, let's try that, and so I'll launch it. And so what's that going to do is it's going to spin up our Dgraph backend, and we'll get a notification once we have the backend up and running. Now, if it's a new region where nothing else is running before, it might take around 7 to 8 minutes to spin up. But for any of the existing regions where Dgraph already sort of exists, it will be done in under 2 minutes. And we're trying to bring down the 7 to 8 minute time window down to 2 minutes, because ultimately that's the goal that we have, is that wherever in the world that you might want, Dgraph can be up and running in under 2 minutes. All right, our cluster is up and running in Sydney, Australia, and I'll just show you quickly the schema. We haven't set any GraphQL schema. We do have some automatic internal Dgraph predicates exposed here, and we have by default anonymous access. Now I'm going to copy this and I'm going to run some queries, and the way I'll run these queries is to use Dgraph incremental. So we have this thing over here which sets the cloud. So I'll make the graph talk to the cloud interface. The address is, this is the address over here. So I'm going to copy this address. And the other thing is the JOT token. So our JOT token is, I'll do that by going to settings, clicking on API keys, create a new key. This is for increment tool, create, copy it over here. And let's try running that. Oops, the address should be here. Okay, so now it's complaining about schema not defined counter.val. That's because our we haven't defined a schema, and in our settings we have set it to strict schema mode. Now we can make it flexible, but that's going to take a bit of time. So why don't I go to schema and just define it in DQL? So I'll add a new predicate, call it counter.val, make it int. It's already int, and just add it. And it's there. So now I think we should be able to run an update. There you go. So we were able to increment the counter.val by 1. If we run it again, we increment it another time. Now I'm going to run it 1,000 times, just so that there's a steady stream of like queries and mutations happening here on this backend. And now we can actually start to use Jaeger. Now the next thing I want to do is to show you Jaeger, and for that I'm going to click on this thing and go to Jaeger. And for that, the one thing that I had to do in between was to go to API keys and create a new admin API key, and we call it Jaeger. Created that, copied it over, and so in the interface it asked me for it, and I put that in. So now you can see Dgraph Alpha. And you can see server.query, and you can find the traces. It shows you all the queries that are happening. You can sort by the longest first to see which one took the longest. And you have all of this interesting information here, which kind of like gives you an insight into what's happening behind the scenes for what Dgraph is doing. And this is pretty amazing because this allows you to see where your bottlenecks might be, which part of the query could be slower, which part is really fast. And all of this is just directly integrated into Dgraph Cloud, so you don't have to run anything separately. We are already running Jaeger for you, and soon we plan to run other stuff as well, potentially like Grafana, so that it's easy for you to consume some of these metrics too. Now, there's one thing that we can do from here is to upgrade to high availability cluster, and that's a possibility as well. So essentially, and similarly, you have access control lists and so on and so forth. So essentially, what we have tried to do is we have tried to really put together all of the different options that would make it easier for you to spin up not just one instance of Dgraph, but an entire cluster, along with all the relevant services like Jaeger, which is what you need to run a proper backend. There's a lot of other interesting stuff that I haven't shown you in this demo here. There is API Explorer, which shows you which you can use to run GraphQL queries. There's a data visualizer, which we are sort of working to improve. It's going to become a lot more interesting in the next month or so, and allow you to like run a lot more interesting queries here. Lambda functions, which allow you to run your business logic. And Lambda functions actually work quite like the AWS Amazon Lambdas, where you can write your function in right now it's in JavaScript, but we plan to extend it to other languages too. So you can write your business logic in the Lambda functions, which Dgraph calls automatically for you. Rattle right now is an external integration, but we plan to integrate Rattle into Dgraph Cloud as well. Settings wise, we have tried to simplify this quite a bunch. We will continue to work on it and make it as simple as possible to understand. And then finally, for our dedicated instances, in which case, let me go to Mate, they get access to some of this monitoring over here. Again, it's a bit bare bones right now, but we plan to improve it in the next coming month. So that concludes the demo for Dgraph Cloud interface. I'll jump back to talk about Dgraph Rocket release next. Apart from all the work that has gone into Dgraph Cloud, we have also been very busy building new features into Dgraph, and we recently launched Dgraph version 21.03 that we nicknamed Rocket. In Dgraph Rocket release, we have lots of new features that I will talk about now. First off, we have multi-tenancy. Multi-tenancy has been such a heavily asked for use feature for a while now. What multi-tenancy provides is the ability to use the same DRAF cluster across tens or hundreds of thousands of tenants, logically partitioned from each other, so they cannot accidentally or maliciously access each other's data. So it practically works as if you have tens of hundreds or thousands of DRAF clusters, but instead of having to spend all of the resources running all of those clusters, you can just have all of these tenants in the same DRAF cluster. And that's been such an asked about feature for us, and we had it on the roadmap last year as well, but we couldn't get to it. And this year, the team really put together a lot of effort to make it, to build it, to test it, and to make it available in time for Dgraph Rocket release. Next up, we have learner nodes. Learner nodes is a very interesting concept. As you might know, Dgraph cluster works by having by operating in a Raft quorum, Raft group. Essentially, multiple Dgraph alphas would form one Raft group and run elections to figure out which one is the leader, and all the others would become followers. And the leader then essentially replicates data as data gets written across the system. So in this system, in one Raft group, all of the servers are participating in leadership elections. The thing about learner node is that it does not participate in leadership election, which means that it does not need to achieve a quorum, and it does not introduce any delays in all the reads and the writes that might happen. So you can take a learner node and put it somewhere really far away. For example, you could put it in a region which is at least 200, 300 milliseconds away from the cluster, and it would not affect the main cluster. Rather, it would act as, you can make it act as an edge computing device, which is getting all the updates from the cluster, so it can serve local traffic in this faraway remote region. That's one of the really big use cases of a learner node. The other use case of a learner node is to be able to spin up a bunch of these when you expect a spike in traffic, or when the spike in traffic hits you. This sort of gives you this automatic scaling, which is typically hard in a database, but with learner nodes, that is very much possible. So you can spin up these things. You serve you get heavier throughput. You are able to serve more throughput. You get through a spike of traffic, and you can then discard these learner nodes. And so these are two very big useful things. Learner nodes are available again in Dgraph Rocket release, and we would soon make them available in Dgraph Cloud as well. And that would be incredible, because Dgraph Cloud is already available, as we mentioned before, in 16 AWS regions, soon to be like 20 plus AWS regions. So you could have your cluster in US West, but your users sitting in Europe, in Far East Asia, or in Australia could be having learner nodes right next to them, so that you can serve the local traffic at a much lower latency than having them talk to the main cluster in the US. The third feature that we have here is change data capture. A database is never running in isolation. Typically, the updates from the database are being sent over to other systems for various kinds of processings, and capturing these data updates has been a much asked for feature by our community. And we thought, Kafka is extremely popular for this event-based processing and event-based streaming. And so what we did was we took the concept from chain data capture and merged that with Kafka. So Dgraph now natively supports pushing change data capture events to Kafka, so they can then be used by they can be then be shipped wherever they need to be shipped to be used by other systems. And we built it in a way where even if Dgraph alphas crash and they come back, the stream would not be would resume from where it was last. So you might get some duplicate entries, but they would always be they're guaranteed to be in the right order, and you're guaranteed to never lose an update, which is really kind of important to making sure that you always see a full uninterrupted stream coming out of your database. The fourth feature I want to talk about is audit logs. Security is really important to us. From very early on, we introduced TLS communication between client and the Dgraph server, and we even introduced a special data type that I had mentioned before called password. So all the users' passwords can be stored safely in the database without any fear of leaking them in plain text. And we even introduced encryption at rest, I think last year, so that the data before it touches the disk is already encrypted. And there is a data key rotation that happens, that is configurable, that happens every a number of days, and the master key can then be stored in the vault. So we really have gone through a lot of effort to make sure that Dgraph is really secure, and part of that security is also about accountability. And so we recently introduced audit logs, so we can capture all the activity that's happening in the database, so that in case there is any malicious activity in the database, the DBAs and the users would get to know about that via the audit logs. And these audit logs, the way we have built it, they can also be encrypted, so they can be stored safely as well. And this audit log feature is again available in Dgraph Rocket release and would soon be available in Dgraph Cloud. Now we talked about all these features that Dgraph Rocket Release has and would be soon in the cloud. Let me actually demo you some of these features. We'll start with multi-tenancy, and for that I'm going to log into my workstation. Go to Dgraph. We have this tool called Compose tool, which lets us create a Docker Compose, so we can easily run Dgraph cluster. Let me just walk you through that Compose tool. It will run one alpha, it will run 1.0, it will run set it up for change data capture, and also run change data capture consumer. Now, if you remember, change data capture is being pushed out to Kafka. So we're going to push out the updates to Kafka, and then CDC consumer would be a Kafka consumer, which would allow us to see what's happening. --ACL would support access control lists. We're going to set the server's Dgraph instances to have this host name, which is the host name of my workstation on Dgraph's internal VPN. And then we'll add some extra alpha flags to set the audit log output to, let's call it audit. All right, and I'm going to quickly show you the Docker Compose that we have built here. It exposes the 3 ports. We have the volume set up here. We have ACLs enabled. And then we have Kafka image, Kafka consumer image 0, and Zookeeper. All right, so we'll run this. It's the run.sh script essentially compiles a Dgraph binary, and it would spin up all of these containers from the Docker Compose. And so now we have a Dgraph cluster up and running. The first thing that I want to show you is that we can do is multi-tenancy. And the way we'll do multi-tenancy is that we will create a bunch of namespaces in the cluster, and we can then send updates to them for the same predicate, and show that they are not interacting with each other. They are they are essentially acting as logically separated, logically and physically separated. Now, before I go there, let me use a tool here, which we call a Dgraph increment. And the Dgraph increment tool is just something that we're going to use to connect to this running Dgraph cluster and make some updates. So the way Dgraph increment tool works is that it was designed to test out Dgraph's transactionality. So it starts off with the value of 0 and it adds 1 to it and commits it. And so in this case, we ran the tool once, we logged into it. If people notice, because we have ACLs enabled, we have to log in. And so we set the username to root, password to password, and namespace 0 is the default namespace. So we were able to log into namespace 0, which is the default namespace, and then update the counter value from 0 to 1. Now, if you run it multiple times, you will see the counter value is increasing from 1 to 2, 2 to 3, 3 to 4, and so on and so forth, right? Now, let's try something. Let's try to run this on namespace 1. What happens is that we actually get a crash because namespace 1 does not exist. So it complains about invalid username password because namespace 1 does not exist. So the first thing we need to do is to add the namespace. So let me go and add namespace here. So we are talking to Dgraph's admin endpoint, and we have a mutation called add namespace. So we're going to try to run this. And it has created namespace 1. So if I keep running this a few more times, it's going to create more namespaces for us. So every time, as you can see, the namespace IDs are increasing. Actually, maybe it's not very visible. Sorry for that if it's not very visible. Insomnia is a bit trickier to adjust the fonts for. But I just run it 10 times, so we have 10 namespaces up and running. Okay, so we got namespaces 1 through 10. Now, going back to this thing, now if we were to run this counter in this increment once more, let's remind ourselves where we were. So at namespace 0, we are at counter value 5, right? And let's run this for namespace 1. For namespace 1, it has never seen this this thing before, so it is just setting it to value 1. And if you look carefully over here, this is the Kafka consumer. This is doing change data capture. We'll get to that in a bit, but I just wanted to show you that it's actually talking to the same exact predicate counter.val in namespace 1 as it was doing in counter.val namespace 0. So they are both talking to the exact same predicate, but because they're separated by namespaces, they're not seeing each other's values. So a 5 over here would not see the 1. So if I go back and try to increment namespace 0, it would be 6. And if I were to increment namespace 1, it should be 2, which it is. So now let's run a bunch of them. So I'll just do and this command. So basically in sequence 1 to 10, we will echo namespace equals to namespace Dgraph increment, and the every namespace gets its own root and has its own password. So you can create a namespace, and then that namespace can get its own guardians and its own list of users with their own login password. So it's really sort of like separated out. Now let's see. So if we were to run this, okay. So if you look very carefully here, sorry, it might not be as clear. Let me see if I move it over here. Okay, let's go back here. So if you go to with the namespace 1 the counter value was 3 as you because it was 2 before, so we created one more time, it became 3. With namespace 2 it's 1, and all the namespaces from there onwards it is sort of 1. Let's make some changes here. So what we'll do is we'll say dash dash num equals to $I, so that each namespace gets incremented namespace number of times, just so we have a different value for each one of them. Okay, and I'm just going to do a read right now. So RO means read only. So you can see namespace 1 is 4, but namespaces 2 through 10 are increasing, 3, 4, 5, 6, etc. Now let's just run this in a while loop. We'll just run this like that. Okay, so now we are iterating over the namespaces and adding the counter values. What I want to show you in this one is to show you change data capture. So let's go to the right hand side over here, log into my desktop, and we were running a bunch of Dockers. One of them is the Kafka consumer, this one. So I'm going to just focus, follow the logs of Kafka consumer. And as you can see over here, all of the updates to namespaces 1 through 10 are coming over here live. And the values as well, along with the UIDs which were updated, whether it's a set operation or a delete operation, it's a mutation. And so this is getting streamed via Kafka to this Kafka consumer that we are listening to, and basically we are printing it out. And so we're listening to over here, right? So now if I stop doing these updates, then these updates stop too. And let me just do one quick update here, and we remove the true. And we will run it just one last time. Oops. All right, so you can see all these updates to namespaces. Along with the namespace, the value and everything is all coming down to is all getting captured via the change data capture and getting streamed to Kafka, which we are listening to. All right, so I showed you multi-tenancy, and I showed you Kafka streaming of change data capture. Now, next thing I want to show you is audit logs. So for audit logs, we had, let me run this thing again in the while loop, so we will have something to look at. All right, so this is going on. Now for audit logs, we're going to go into the Dgraph alpha instance. And we had asked in our Docker, actually, if I look at, we had asked in our Docker compose that the audit logs should go into the audit directory. So we have an audit directory created over here, and let's just follow the audit logs. Audit logs are a bit more complex to read compared to the change data capture, because that's a lot more simple. But if you look at the audit log very carefully, let's look at one of them. Actually, let me just print out. So we can look at one of them really carefully. Let's look at this one. It starts with the timestamp, so we know exactly when this event happened. It knows the endpoint that was called, which is Dgraph query. It mentions which user was logged in. In this case, Groot, which namespace the user was from, the server which they accessed, and the client IP address along with the port where we ran the commands. And it mentions, like, which method did they use? Did they use gRPC or HTTP? So in this case, it is gRPC. It mentions what was the request. So in this case, it was a mutation. So it mentions the exact mutation. It mentions the value that they set, and the fact that it was meant to be commit set to true. And then in the end, it mentions whether this mutation was successful or it failed. In this case, it was successful, therefore status was okay. Now, let's do one more thing. Let's just create one more namespace. So I did create namespace 11, and let's see how it affects the audit logs. So they might have, let's see, unauthorized user. Let me run that again, just so that I get a clean log here. There it is. So as you can see, we ran the add namespace query, and it was run as root of namespace 0. In fact, the guardians of namespace 0 are the only ones who are allowed to add or delete namespaces. So in this case, we captured the audit log captured the time, who was logged in, from which client IP address, the request that they ran, and whether it ran successfully or not, and it did. So that shows the audit logs. The last thing I want to show you guys. Now for the last part of this, I want to show you learner nodes. And for that, I'm going to just run the Dgraph cluster again. So while it's getting set up, I will pick up a Dgraph Corp machine, which is all the way in India, and I will show you the ping latency of that machine. So it's a machine called dginbravo.corp.dgraph.io. And as you can see, the ping latency from my workstation here in the US to this machine in India is 250 milliseconds. And what I'm going to do is I'm going to log into that machine. And as you can see, it's already a bit slow. And I have Dgraph binary copied over here. Remove the P, T, and W. Remove the previous directories. And I have Dgraph binary over here. Our cluster is up and running here. So the ping latency, as you can see, is pretty high. I will run Dgraph implement tool here. And let's not, actually we might still need to log in. So password equals to password, but we'll just use namespace 0 in this time. And I will set the wait to 3 seconds. Okay, because we just restarted this cluster, it started from scratch, so the counter value is back to going from 1 to 3. All right, so this increment is going on, and at the same time, let's start the Dgraph cluster, Dgraph learner node here. So we'll set draft equals to 1, idx equals to, let's say, 101, and learner equals to true. My address here would be tginbravo.com with the 7080 port, which is the gRPC port for alpha internal, and the 0 it should connect to would be the 0 of the main Dgraph cluster running in the US. So that would be on my workstation, which, and the 0 port is 5080. So I think this should run our learner. Let's see. Okay, so what this has done is that it has gone and asked the zero leader, connected with zero leader, gotten the state of the membership, and then went and connected with the group 1 leader. And the way the learner nodes work is that they pretty much can do all the stuff that a normal alpha can do. The only thing that they don't do is they don't participate in elections, so they don't end up slowing down the quorum achievement for the main cluster. So if you look at the conf state that was set for this group one, is that it has one node, which is the main node, which participates in elections, and then we have the learner 101, which is only a learner node. Now let's log into this machine again to get another terminal here, and what we'll do is we'll start to read the dgraph increment. We'll run the dgraph increment so we can read the updates that are happening. And let's say num equals to 1000 and best effort, and we need to set the alpha equals to djain.bravo.core.dgraph. And think of it as a local client that's running in India itself. So what is happening over here is that it's doing a best effort query and talking to the alpha that is running over here and getting the value of the counter directly from this alpha in India. And you can notice that by looking at these latency numbers. So the time it takes to query is only 2 milliseconds, which is pretty much like, it's on the same machine. Now, if you notice these numbers over here, so it's 65 and 66. Actually, let me move this over to this so we can see both of them together. So this is our main workstation, and this is our DG which is the India machine. And as soon as they have updates over here, the updates pretty much get reflected immediately. Let me increase the frequency of this instead of waiting for, just waits for 0.5 seconds. So we are 76 and immediately 76 gets reflected, and we have 77 gets reflected, and so on and so forth. Now we'll do one thing. We will, instead of doing a best effort, we'll actually just let it run some updates. So now what it's doing is that it's actually trying to increment the counter. And as you can see, it's having to talk to the Dgraph cluster all the way in the US. So the latency numbers are pretty high here. The query took 230 milliseconds, which is exactly the kind of ping latency that we see, and the mutation took double of that. So overall, the server took 600 milliseconds to execute these writes. And this is the same counter, and you know that because you can see that this one got 100, and this one actually got 100. This one got 100 and 101, so this one did not see 100 and 101 because of the transactionality. Only one client can see each number. And so you can see the huge latency distortion here. But then if you make it just a best effort is eventual consistency read locally. It happens really fast. It happens really fast, and it can see the updates. So that way, now if you have essentially a client in India, it can get the updates from the US cluster while it's connecting locally to the client in India and can get really great numbers, latency numbers. So that concludes the demo around learner nodes. And I'll go back to the slides now. Thanks. Now that I've shown you a demo of all the features that we have built so far in this year, I'm really excited to share with you the roadmap that we have for the rest of the year. And the roadmap for this year is really built around two things. One is performance optimization, and second is ecosystem integration. So talking about performance optimization, Dgraph query performance is already really good, but the fact is that we don't even have a query planner right now in the system. And so what we want to do is we want to build a really solid query planner so we can really optimize the queries even way further than where they are today. Already, as you saw, we are already beating our competition 2 times to 20 times in query execution. But with these upcoming changes around the query planner and query optimizations, we feel that the difference would widen significantly. That's one part of the equation. The second part of the equation is that the data loading speed. We already have a commit in our main branch where we have double the speed at which data can be loaded into Dgraph, and we have more changes coming in, which we expect to further double the speed by which data can be loaded, and that would make really easy for our users to bring in large amounts of data into Dgraph, and then be able to run really complex queries extremely fast. So we're really excited about that. That's one. The second thing is around ecosystem integration, and what we have seen is that a lot of our users are migrating from SQL database or a MongoDB or other graph databases, and to support this, we'll be introducing automatic migration paths, automated migration paths. We'll focus on the Dgraph Cloud first, and the experience that we want for our users should be that they would upload their exports from the database or potentially point Dgraph Cloud to their database, and we will take care of the entire process of migration into Dgraph for them. And we also want that if they have a system already running which they cannot completely migrate over to Dgraph, we will be able to take a live stream of updates from that other database into Dgraph, so Dgraph can become the unified data store and become the unified graph platform for your application. And the important thing here is that by allowing migration and allowing streaming of data from these different data silos, whether it be a SQL database or a MongoDB or whatever other databases that might be, or other data sources that might be, by pulling them into one graph platform, we get to the most important use case for Dgraph, which is data unification. Now, if you go back to the inspiration for Dgraph, that was that we had this big knowledge graph, and we had these fragmented backends, each with their own data models, which were running separately. And the big thing that we wanted to do at Google was to be able to unite everything into a single graph platform. And that's exactly the kind of use case that we see other people, our users, doing with Dgraph as well, is that they take data from all of their vertical data silos, which they probably can't even run queries across easily, and put all of that into Dgraph, making it the unified graph platform, so that they can then run really interesting queries across it, really complex queries, be able to traverse relationships and identify interesting patterns and surface that to the users. And that is the big underlying vision that we have for Dgraph Cloud, is to become the cloud graph platform which you can rely upon for running your microservices, for dumping all of your data, for serving user traffic, and for all of the interesting use cases that are possible when you can unify your data. Thank you.